In the previous class, we have solved certain problems on time domain specifications, what kind of problems that appear in competitive exams. So, these time domain specifications are about 5, and if you recall, it is delay time, rise time, peak time, settling time and peak overshoot. All these 5 come under transient part of time response, and all these time domain specifications depends on damping ratio and undamped natural frequency. So, this is given by 1 plus 0.7 zeta by omega n delay time, and rise time is pi minus cos inverse zeta by omega d, and peak time depends on omega d, and settling time depends on time constant. This is given by 4 by zeta omega n default for 2% tolerance, and the peak overshoot is given by e power minus zeta pi under root of 1 minus zeta square. So, if you look at all these 5 domain specifications depends on either zeta and omega n. Only this peak overshoot does not depend on frequency of oscillations, but it depends on zeta. Now, let us see that what is the effect of moving poles on all these time domain specifications. We can consider 3 cases in this effect of moving poles. In that, number 1, say the poles are in the complex plane with this complex conjugate pair. So, it has some real part and then it has some imaginary part. Call this pair as 1 and 1 dash. Now, let us assume that these poles are moving vertically along this j omega axis. This is real part of S plane. So, if the pole moves to the new position vertically, that is 2 dash, and further it moves to 3 and 3 dash, then what is its effect? Moving the poles vertically along j omega axis on this time domain specifications. If you see that this part, this is origin, and this part is reflects as a time constant. So, there is no change in the real part because we are assuming that poles are moving vertically. So, if the poles move vertically along j omega axis, then there is no change in the real part, means the tau is constant. So, we can say that the settling time Ts is given by 4 tau or 4 by zeta omega n, it remains constant. So, there is no effect on settling time, it is the time required for the response to settle the output, to stay in the stable region, in the steady state part. So, there is no change in the settling time, so Ts is constant. This is the first effect of moving poles along vertical axis. Now, the second one, as you see that this part is called as omega d, damped natural frequency. So, this omega d is increasing. Now, as the poles, we assume that here they are moving vertically. So, when 1 has become 2, then there is a change in the damped natural frequency from omega d1 to omega d2, and further increase will have omega d3. So, there is an increase in the damped natural frequency. So, when omega d is increasing, you can see that rise time, peak time, it goes down. So, the effect of moving poles vertically upwards increases the damping frequency. So, rise time and peak time they go down, and no change in the settling time, as I said, because it depends on the time constant. So, the real part of the pole. So, there is no change in the real part of the pole. So, settling time remains constant, no effect, but rise time and peak time gets reduced because omega d is increasing when poles are moving vertically. Now, another important parameter, that this angle with respect to the real axis is known as theta. So, there is an increase in the angle when poles are moving vertically, there is an increase in the angle. So, the zeta and theta, they are actually related. So, when theta is increasing, the zeta goes down. So, that is the relation between theta and zeta, because cos theta is zeta. So, as theta is increasing, the zeta goes down. So, when zeta is decreased, because of the movement of the pole vertically, the peak overshoot will increase. So, the system becomes less stable. So, the decrease of zeta causing peak overshoot increases and stability is affected with the movement of the poles vertically. So, three things you need to observe here, A, B, C. One is real part is constant, so no change in the settling time, and rise time and peak time goes down because omega d is increasing. You can look at the expression, and zeta is decreasing because angle theta is increasing. So, that is affecting the peak overshoot. So, there is a rise in peak overshoot is not a good sign, and stability got affected when poles are moving vertically in S plane. Now, we look at the second case, when the poles move horizontally. So, we have seen the case like when the poles move in S plane vertically, it is affecting the peak overshoot because there is a decrease in zeta. So, peak overshoot is greatly affected, and so stability of the system also got affected. So, there is no change in the settling time because that real part of the pole is not changing. This is the real part. So, there is no change in the real part. I said the settling time is constant because time constant, real part of the pole depends on time constant. Now, Tp and Tr, they depend on omega d. So, there is a increase in omega d. So, the rise time and peak time are reduced. So, how do we represent in the time response? If you see the waveform for step input, the response, this is unit step, then the response will be like this. And this is the settling time required for the response to reach and stay within the 2% tolerance limit. Now, when you see here, no change in the settling time when pole move towards up, but because of the increase of omega d, there is a reduction in the rise time and peak time, means the waveform comes closer this side, but no change in the settling time. And also there is an increase of peak overshoot because zeta is decreased. So, the waveform, this is the peak time, as you know, time required for the response to reach the highest peak. Now, that peak time got reduced because of increase in omega d from omega d1 to omega d2. So, you need to represent this way, increase the peak overshoot, but peak time should be reduced, but no change in the settling time. Settling time is same for both the waveforms, but you can observe now this is the peak time for the first case, omega d1, poles are here. Now this is the peak time. So there is a reduction in the peak time, but there is an increase in the peak overshoot. You can see that this is the peak overshoot and this is the peak overshoot. Okay. So peak time is reduced, but peak overshoot is increased when the poles are moving vertically. Further increase of pole vertically, it comes closer now this way, but settling time there is no change. For all the three waveforms, you can see that this is Tp3. So Tp3 is very less, Tp2 then Tp1. So peak overshoot, if you see, there is an increase in the peak overshoot for further increase of the pole, but peak time got reduced. That way the rise time also, there is a reduction in the rise time. So that is a good sign. This is the case of poles moving vertically in the S plane. They are not affecting the settling time, but rise time and peak time got reduced, but peak overshoot is badly increased. So zeta decrease causes peak overshoot rise, and the stability got affected because of the poles moving vertically. Now let us discuss when the poles move horizontally, what will be the effect on this time domain specifications. Now let us see that this is the origin. Originally the poles are here, 1 dash. Now let us say that these poles are moving horizontally to the new position, 2 dash, 3 dash. Now let us see the effect of moving the poles horizontally on this time domain specifications. First part is what is happening to the real part of the pole. So real part of the pole is moving towards left. So there is an effect on time constant. So this is imaginary part and this is the real part of this. So because of the poles moving horizontally away from j omega axis, there is a reduction in the time constant. So the settling time depends on the time constant. Generally it is 4 tau. So as time constant reduced when the poles are moving left, the settling time is reduced. So this is a good sign that the time required for the response to reach and stay within the tolerance limits got reduced. Now you can see that second effect, that imaginary part is not changed, means omega d is constant, no change in omega d. So when omega d is constant, you can see that rise time, peak time, they depend on omega d, so that remains almost constant. So no change in the peak time because the omega d is constant. Now the third part, what happens to the theta and zeta? You can see that this is theta 1, now this is theta 2 and this is theta 3. So there is a reduction in the phase angle from 1 to 3. There is a reduction in the phase angle, so that will increase zeta because theta is equal to cos inverse zeta. So there is a reduction in theta causes the zeta increase. So when zeta is increased, the peak overshoot will be reduced. So that is the effect here. The peak overshoot is reduced because increase in zeta. So the stability is improved. The stability is improved in this case. Moving the poles horizontally improves stability, reduces the settling time, but not much affected on rise time and peak time. Now let us see the third case, that when the poles are moving inclined, neither horizontal nor vertical, but they move with some inclination. Now the last case, that the poles move with some inclination. Originally they are here with 1 dash. Now they move in this way, 2 dash, 3 dash. So poles are moving neither horizontal nor vertical. Now the first part, what you should see here is, this is the real part of the pole. So the real part of the pole is increasing, makes the time constant reduction. So it reduces the time constant as the pole move away from the imaginary axis. So this causes the settling time to go down, because settling time depends on tau, time constant. Now the second one, what happens to the imaginary part, omega d1, omega d2, omega d3. So there is an increase in omega d, so the rise time and peak time got reduced. So there is an increase in omega d, so rise time and peak time reduced. Now what about theta, the angle with respect to the real axis? There is no change in the angle because poles are moving along a fixed angle. So no change in the theta. Theta is constant, means zeta also constant. Zeta is constant, so peak overshoot, no effect on the peak overshoot. It remains same as it is, whether the poles are here or here or here, it does not have any effect on peak overshoot. So no change on the stability point, no change in the stability point of view when the poles are moving in some inclination. So we can make conclusion that in S-plane, if the poles move along real axis vertically, stability got affected, stability becomes worse, and when the poles move horizontally, the stability is improved, and when the poles are moving with some inclination, no effect on the stability, So always you remember the peak overshoot, when there is a rise, we say it is not a good sign, but there are some limits for peak overshoot. It should be between 5% and 40% peak overshoot. So if it is greater than 40%, the peak overshoot is greater than 40%, then system becomes unstable, and if it is less than 5%, we say that the response is very slow. There are two aspects to see in the time response, one is stability and the other one is slow response. So if it is less than 5% peak overshoot, we say that the response is very slow. If it is greater than 40%, we say that system stability is a problem.